Hello. So, in this lecture, we are discussing on rate of reactions. Rate of reactions, the reaction rate or rate of reactions is the speed at which chemical reactions takes place. It is defined as proportional to the increase in the concentration of product per unit time and to decrease in the concentration of reactant per unit time. For example, you take rusting in iron. So iron rusting as a slow reaction rate, the process is slow. Iron is degrading and it will become a powder. Combustion of food is a fast reactions. So these reactions are depends on time. The reaction rate we are measuring with respect to time. Reaction rate are changing. The concentration of the reactant is decreasing with respect to time, and concentration of the is increasing product increasing with respect to time. So so we are measuring the rate of reaction with respect to concentration of reactant with respect to time, or concentration of product with respect to time. So reaction rate can be determined by measuring the change in concentration over time. Chemical reaction is a part of physical chemistry that concerns how rate of chemical reactions are measured, how to measure the chemical rate of how past chemical reactions is takes place, that one measured and predicting how the reaction rate can be used to produce reaction mechanism, probable reaction mechanism. To predict the probable reaction mechanism, we are using a rate of chemical reactions. We are measuring the rate of chemical reaction. We are predicting and we are finding the probability of mechanism. What is the probable mechanism? How the rate of reaction is takes place. The concept of chemical kinetics are applied in many disciplines. What are the disciplines such as chemical engineering, enzymology, environmental engineering? This is applied in chemical engineering. It is applied in enzymology. This one applied in environmental engineering. So the study of chemical kinetics includes the rate of chemical reactions and rate loss, the factors such as temperature, pressure, concentration, and catalyst influence the rate of reactions. The mechanism or sequence of step by which chemical reaction is takes place. This will give knowledge of rate of reaction is very valuable to understand chemical reaction. It's also of great importance in selecting optimum condition for industrial process so that it proceeds at a rate to give maximum yield. So it gives optimum conditions of rate of reaction. So where, in which condition, in which temperature, which time, the maximum reactions take place, it will give one idea. It is give one steps. It is gives one procedure. It is gives one uh, conditions, optimum conditions that the rate of reactions is takes place. More rate of reactions takes place and more product we are getting. Factors influencing the rate of reaction: temperature. At higher temperature, more molecules have a greater, more molecules have a energy greater than the activation energy. There are more collision. Both reaction, both increase the rate of reactions because molecules have more activation energy at higher temperature. More collision is takes place. Due to that increase in the rate of reactions is increases. Concentration. Higher the concentration, greater number of collision, greater the rate of reactions. If concentration of molecules are more number of collision is take place and it increases rate of reactions. Surface area. The greater the surface area of electrode or materials, solid materials, and any surface, greater area open for reaction. More area is there for reacting molecules. Therefore, it increases rate of reactions. Next one, catalyst. A catalyst provides an alternative pathway for a reaction, which has a lower activation energy than original value. That is in the absence of catalyst. Therefore, at a given temperature, more molecule can react than the catalyst when the catalyst is absent. So it indicates that catalyst provide alternative path. It gives a different path in which has a lower activation energy than original route. Therefore, it given at a given temperature, more molecule can react than when the catalyst is absent. What happened to the reaction of A as time goes by? So here is the A is the reactant, B is the reactant. It will give a product. So A is decreases. You can observe here. A is this is the A, this is the A, this is the A, this is the B round one. These two are reacting. After 15 minutes, there is a product. Around four products are there. These molecules are decreased. A and B decreases. You can observe that. After 30 minutes, you can see A and B reactants are decreasing. The product is increasing. After 45 minutes, you can see that fully converted AB is converted into the C product. Like the concentration of A is decreases with respect to time. A, B, C. As a reaction proceeds, the concentration of A decreases. Rate of change can be defined in the terms of A decreasing. Rate is equal to minus change in concentration of A with respect to change in time. Here a negative sign is there because A is decreases. Negative sign needed because change in concentration is negative. Rate must be, we are always telling rate must be positive. That is the reason we are planning to take, if we take a product one, the rate is positive. If the rate is defined as C, we have no negative sign. Yes, is needed. You see, rate is equal to delta C divided by delta T, change in constant formation of the product divided by change in time. So this equation we can use for measuring the rate how fast a reaction is takes place. It is the same diagram which I explained previously. You can see in this graph graphical representation of rate of reactions. In the y-axis, concentration of substance in molar concentration. In x-axis, time in seconds. X-axis 5 seconds, 10 seconds, 15 seconds, 20 seconds, 25 seconds, 30 seconds. In y-axis 0, zero point 0.1, zero point 0.2, 0.3, zero point 4. The reactant A is decreases with respect to time. You can observe here this black color 1. So 5 minutes it decreases the concentration. 10 minutes decreases like that. 10 seconds, sorry, not minutes. And also you can see this product concentration increases with respect to time. Is the rate of the reaction constant during the course of reaction? No. Answer is no. Okay. Next thing. Therefore, calculation of rate using the change in concentration formula will give different results depending on what time interval you choose. Making a intervals time smaller, we can calculate the rate of reaction at a specific instance in time. If we take a small time, we can calculate the rate of reactions. You can see in this one, same diagram, concentration of substance. So you can see this is versus time in second. You can see slope is decreasing with respect to time. Slope of tangent line will give the instantaneous rate at a given point in the reactions. Note, note again that reaction rate is not constant. It decreases with time. It is not constant. You can see if we measure rate here, it is more. If we measure rate here, it's less, it is less. So rate constant we can also measure by using coefficient. So A concentration of A substance, B concentration of B substance like this. For measuring the rate, we can also use coefficient equation. Rate is equal to, you can see for writing this one, 1 by small a into delta A capital A divided by delta T is equal to minus 1 by B into delta capital B and the delta small t is equal to here plus. See, there's a plus. Right side one is plus 1 by C delta capital C into delta small t. So is equal to 1 by D delta capital D delta small t. So we can also measure concentrations using what is this? This is using rate equations. This is the equation. This is the chemical reaction for the reaction. For this reaction, the value of delta BrO3 minus by delta T is equal to 1.5 into 10 to the power of minus 2 meter per minus 2 moles per second at a particular time. What is the value of delta Br delta T at the same time? So they given rate constant of this one. Rate is equal to this one they given. We have to write this one delta Br O3 minus by delta T. This is equal to this one is equal to minus delta bracket by R minus by delta T. It is written 5 here. We have written here 5. Then we want what is the value of this one? What is the value of this one? So that's the reason what we are doing. We have put a 5 multiplied here 5 and multiplied both side 5. So what will happen? Here 5 get cancelled. Then if you multiply these things 7.5 into 10 to the power minus 2 moles per second is the value of this one. Like this, we can calculate the values values of the reactions, rate values of the reactions of different reactants, rate of change of react. So next one is rate law. Rate law expresses the relationship of a rate of a reaction to the rate constant, relationship to the rate of reactions to the rate constant, and concentration of reactant raised some power. This is the rate equation, rate expression. For a reaction, small a, capital A, small b, capital B is equal to small c, capital C, small d, capital D. X and Y must be experimentally determined. This one we have to determine experimentally to find out this reaction. Because order of reaction we have to experimentally determine. We can't find out by using equations. We will learn how to determine X and Y later. We'll, we'll clearly we can understand later how to determine X and Y. For now, let us look some example of reaction and rate laws. So now you see this graph rate that is meter moles per second in y-axis. In x-axis, the concentration. As the concentration increases, rate also increases. So you can see this. Note that straight line. A linear relationship can be written. Rate is directly proportional to the concentration. Concentration increases, rate is also increases. Rate is equal to K a to the power of 1. The concentration is increasing. So rate is equal to K constant, rate constant, bracket here. K is called the rate constant. K as a units. It is obtained by solving the equation for K. See, you can put if you put a K here and rate, we can get a K value. It's mole concentration, it's moles per second. If the rate is known, A is known, a value for K can be obtained. Every time this reaction takes place at a constant temperature, same value curve. If it is a constant temperature, then value of K is same. If temperature change, value of K constant is also changes. You can see for the reaction, this reaction that is the NO, the gas reacting with hydrogen gas. It gives nitrogen and water. Rate law determined to be rate is equal to K NO2. 2 hydrogen is there. Reaction said to be, what is the order of reaction? Order, second order in NO, first order in hydrogen, third order overall. The sum of X and Y is equal to 3. Order can be 0 sometime when the concentration does not affect the rate. It is this concentration does not affect the formation of this product, then order is 0. Sometime order can be a fraction, sometime 3, sometime 1, sometime 2. We have to determine experimental. So order determination, we have to conduct the experiment. How to conduct the experiment? To conduct the experiment means we have to take a nitrogen gas, nitric oxide gas, that not nitrogen, react with a chlorine gas. The equation is given: nitric oxide gas react with chlorine gas, it will give NOCl. The following initial rates of a reaction have been measured for the given reagent concentration. So this is the rate: 1.19 moles per hour, 4.79 moles per hour, 9.59 moles per hour. This is the concentration of molar: 1.25, 1.5, 1.5. Chlorine is 1.5, 1.53. So if you want to find out rate of the reaction, for example, if you want to find the rate of this reaction, so which one is a constant? This is the constant. You see this one. One reactant is constant. We are varying these two reactants. So what is the rate of the reactions here? Per x rate, the the fluorine is kept a constant. So here chlorine is kept a constant here. Rate ratio of rates. If you take a ratio of this one, what is the ratio of rates of NO? Ratio of rates. What is the ratio of rates here? 4.79 rate 2 by rate 1. And ratio of concentration is equal to ratio of concentration. What is the ratio of concentration of NO? That is 1.5 to 1.2 is equal to 2. Then we can tell that what is the rate of the reactions of NO. We have to find out the order of the reactions here, NO. So NO is equal to, it is a 4, 1.19 divided by 4.79 divided by 1.9 is equal to 4. 1.5 divided by 1.2 is equal to 2. This is a 2. It is written X here. X is equal to 2. The order of reaction for NO is 2. Then, then you see this. So here in this condition, NO kept a constant. Then we can find out order for chlorine. So rate of reactions, that is a rate 2 divided by rate 1. That is rate 2 is 9.59 divided by 4.79. That is a rate 2. Rate 3 is 9.59. Rate 2 is 4.79. It gives a 2. Rate of concentration, it is a higher concentration. That is a rate 3 concentration 3 and rate 2 concentration 1.5. It is a 2. 2 is equal to 2. Then y is equal to 1. Y is power. We have to find out the y. It is equal to 2. Then what is rate is equal to K, what's order? NO2 and chlorine 1. We can get order of overall order of reaction is 3. Like that, we have to find out order of reaction by using experimental results, not by any equations. Integrated rate law. Rate law can be measured to determine the concentration of reactant at a given time during the course of reactions. We can look at some simple cases: first order overall, second order overall, zero order overall. First order kinetics for a reaction, first order kinetics, A is changing to product. That rate is equal to K, that is K into A because it's first order. So rate is equal to minus delta A, capital A divided by delta T because coefficient is 1. This is gives us delta A by delta T is equal to Ka. The previous equation, this equation, when it is calculus is applied for this one, we will get a equation ln capital A divided by ln capital A naught. Initial, this is initial concentration at 0 time. This is the A at that time is equal to T. This gives minus KT. Then when you simplify this, rearrange this, ln A minus ln A naught is equal to minus K. When rearrange this, you will get a ln A is equal to minus KT plus ln A naught. This is similar to y is equal to mx plus p, slope intercept form. Therefore, plot ln A versus time gives a straight line with a slope minus k. So order of reactions plots concentration of A with respect to time. This is, it decreases like this. Ln A versus time, it gives a straight line. The slope of the first order reaction is minus k. K is the rate constant. So order of reaction, first order of reaction, you have to take ln NO205 versus nitrogen pentoxide versus time. You will get a straight line decreases with respect to time. Change slope, we have to take a slope, change in y delta v divided by delta x. So what is the difference? You can see minus delta minus highest value minus 1.5 minus minus of 3.4, that is 40.5 minutes minus 6.7, we'll get a slope that is minus k. Then it is changes to minus of minus, it will change to positive, that is 0.034 minutes. So then problem, there is one problem how to find out the rate of reactions and something related to first order reactions. There is a one reaction SO2 and Cl2 gives to SO2 and chlorine gas. Decomposition of SO2 Cl2 produces SO2 gas and Cl2 gases at a certain temperature. The concentration of sulfur SO2 Cl2 was monitored as a function of time. A plot of ln SO2 Cl2 versus time in second produces a linear plot with a slope intercept equation given as, you see, this is the equation they given, y is equal to minus 0.00310 x minus 2114. What is the order of reaction? What is the order of this reaction? What is the rate constant? At the same temperature, there is another question is there. A 0.200 molar SO2 Cl2 is decomposed. What is the concentration of SO2 Cl2 that remains after 5 minutes? What's the concentration of SO2 Cl at that time? Also, fourth question is there. For the first question, so if you plot LAN SO2 Cl2 in taking y-axis, in x-axis, we are taking a time in second. If it is gives a linearly decreases like this, that gives the first order. This indicates first order of the reaction. The slope, if you take a slope of this reaction, this gives the rate, that is the rate constant, K, that is minus 1.3.1 into 10 to the power of minus 4 per second. That is 1 per second. It's the rate it is giving. So this is the rate at the same temperature, a 0.200 molar SO2 Cl2 is decomposed. What is the concentration of SO2 Cl2 that remains after 5 minutes? This is a 0 SO2 Cl2 after time. This one is minus K. So how much X it is formed? So Cl2 how much is there? How much is decomposed after time? Just for measuring that, we are putting this K value here, and this is the unit 1 by seconds per first order reactions. So here 5 minutes we are putting, 5 minutes we are converting into seconds, that is a 60, 5 minutes into 60 second divided by 1 minute, per 1 minute 60 second, right? So then we are taking this ln, removing a ln by exponential, applying exponential on both sides, we can remove this and we will get this x value. Exponential of this value is 0.1911 and x this one, therefore x is equal to 0.180 molar. Like this, we can calculate the remaining concentration of SO2 Cl after 5 minutes. So after that, only we have solved 3 questions here. Remaining questions we can solve. That is the you can do like that. We can also find out the concentration of reactants, the first order. Last one in this concept is first order kinetics and half-life. Half-life, there is a T of the time required for the concentration of reactant to decrease to half of its initial concentration. That is T of A is equal to half A naught. For the first order reaction, we have ln A by A naught is equal to minus small kt. You substitute this one, A is this one, A get cancelled, A naught. Then ln half is equal to minus kt half. It gives this ln half is equal to 2. Then it is gives kt half, that's plus kt half. Then t is equal to 0.693k. You can see this ln minus that equation. So this is the equation we are using. T of is equal to 0.693k. This is the half-life equation for first order reaction. Note that it is independent of concentration. We can see we don't have any concentration here. It does not matter how much you start. Does not matter how much you start with the amount of time it takes to cut the amount to half is always be a same. Means what is the meaning of this? Means if we take this one is 8 in this ball, a concentration with respect to time, this graph. Yes, 16 small balls are there, then it is decreases 8, then decreases half, then it is decreases 2, like that it is rate of reactions is changing. So last problem. So like that the half reactions are changing. So that's the reason it's not depends on concentration. So in the first order reaction started with 8 molar of substance A and half-life was first unit. What is the concentration would remains after 3 minutes? So first is 8 minutes, then it is cut to 4 minutes, then it is changed to 1 minute, then it is to 2 to 1. After 3 minutes, it's 1 molar concentration. So the first order reaction as a rate is equal to 3.0 into 10 to the power minus 3 seconds. What is the time required per reaction to be 75% complete is T of is equal to 0.693 divided by 3 into 10 to the power minus 3 second. So it will gives 231 seconds, 2.3 into 10 to the power 2 seconds. Like this, we can calculate of the half-life of the reactants to formation of half, how much time it's required. Exactly half of the concentration. Thank you. We have explained today rate of the reaction, introduction to rate of the reaction, and factors affecting on rate of the reactions, and order of reactions, first order of reactions, and how to determine order of reaction in experimentally from the calculations we have explained. And then we have discussed about rate law, first order of reactions. We have discussed the first order of reactions. We have found out integrated equation. Then integrated equation. From the integrated equation, we can use for calculation of rate constant, rate of reactions. Also, we can calculate concentration of reactant. Also, reactant or product. Also, we can calculate. Then we have discussed half-life half-life of reactant, time taken for half of the reaction, half-life of the reactant means it is exactly reactant changing to half. What's the time it required? We can calculate it by using equations. So I will stop here.